Have you ever really stopped to think about hearing? I mean, how a simple vibration, just a ripple in the air, somehow becomes the soaring notes of an orchestra or the familiar sound of a friend's voice. Well, in this explainer, we're going to follow that incredible journey, from a simple sound wave all the way to a conscious thought inside your brain.
Right? That's the big question we're tackling. We're going to break down the absolutely incredible biological process that transforms raw physical energy into the rich, detailed, and meaningful soundscape of our lives.
So, here's our game plan. We'll start with the basics of sound itself, then dive into a fascinating scientific debate about pitch. After that, we'll discover our brain's built-in GPS for sound, understand what happens when hearing goes wrong, and finally, we'll put your new knowledge to the test.
First up, let's talk about the anatomy of sound. You know, to really get how hearing works, we first have to understand what it is we're actually hearing. And it all boils down to waves.
Okay, so the first key ingredient of a sound wave is its amplitude. It's really just a fancy word for loudness. A whisper, that sound wave has a very low height, but when someone shouts, that wave gets way taller. It's carrying more energy, and it hits your ears with a lot more force. That's amplitude in a nutshell.
Now, we measure this loudness in the real world using decibels, or dB, and these numbers tell a really important story. A whisper is a gentle 30 decibels, no problem there. But everyday traffic noise, that can hit 85 dB, and if you're exposed to that for a long time, it can actually start causing damage. And blasting music at full volume? You could be pushing 110 decibels, where hearing damage isn't just possible, it's very likely. It's a pretty powerful reminder of how physical these sound waves really are.
The second key property is wavelength. So if amplitude is how loud, then wavelength is how high or low the sound is. Think about a guitar string. A short, fast vibration creates waves that are all packed tightly together. That's a short wavelength, and it gives us a high-pitched note. A slower vibration from a big, thick string creates waves that are stretched way out, and that gives us a deep, low bass note.
So our ear is getting hit with all these waves, different loudness, different pitches. But how in the world does the brain make sense of it all? This very question sparked one of the biggest debates in the science of hearing. Two major theories stepped into the ring: place theory and frequency theory. Place theory says it's all about location. Different pitches tickle different spots in our inner ear. Frequency theory, on the other hand, says no, it's all about timing. The pitch is determined by how fast the nerve impulses are firing off to the brain. Let's dig into place theory for a second. I want you to imagine your cochlea, that's the little snail-shaped part of your inner ear, as a rolled-up piano keyboard. According to this theory, a high-pitched sound, like a whistle, only activates the keys right at the entrance. But a deep bass note, that sound wave travels all the way to the very end, stimulating the keys deep inside. So the brain just has to know which location is buzzing to know the pitch. Pretty neat, right?
It's an elegant idea, but it isn't the whole story. Frequency theory had a different take, and scientists, being scientists, designed a really clever experiment to see if it held up. This is where we get to see science in action.
The hypothesis they started with was beautifully simple. If you play a sound at 200 hertz, which just means the sound wave is cycling 200 times every second, then the auditory nerve should fire exactly 200 times per second to match it. A perfect one-to-one relationship. So to test this, researchers brought in 50 different participants. They hooked up some specialized equipment to measure the exact firing rate of their auditory nerves while they played different tones, all to see if they could find that perfect match.
And here's the twist, the part I love about science. The hypothesis? It was wrong. The data just didn't support it. That clean, simple idea of a perfect match, well, it wasn't what was actually happening inside the human ear.
So here's what the evidence actually showed. When participants heard that 200 hertz tone, their nerves didn't fire at a neat and tidy 200 times per second. No. The firing rates were all over the place, ranging from 180 to 350 impulses per second. This was huge. It proved that our brain doesn't just listen to one neuron firing in perfect time. Instead, it seems like it's listening to a whole team of neurons firing together. The truth, as it so often is, was a lot more complex, and frankly, a lot more interesting. So, the brain is doing all this incredible teamwork just to figure out pitch. But that's not all. It performs another amazing trick. It acts like a biological GPS system, telling us exactly where a sound is coming from in 3D space. This is called sound localization, and your brain does it using two tiny but absolutely critical clues. the minuscule difference in the time it takes for a sound to reach each of your ears, and the slight difference in how loud that sound is when it gets there.
And this is a brilliant survival skill. I mean, think about it. You're walking down the street, a car horn blares out to your left. Your brain instantly, and I mean instantly, calculates that the sound hit your left ear a fraction of a millisecond sooner and was a tiny bit louder than in your right ear. Without even thinking, you know exactly where that danger is coming from. It's incredible.
Now that we've seen how this amazing system is supposed to work, let's take a look at what happens when parts of it break down. Understanding hearing loss is really all about figuring out where along that chain the signal fails.
Hearing loss usually falls into two main buckets. First, you've got conduction deafness. Think of this as a mechanical problem, like a buildup of earwax that's physically blocking the sound waves from getting through. The good news is, this is often treatable. But then there's sensorineural deafness, and this is different. This is damage to the delicate inner ear or the auditory nerve itself, often from things like loud noise or just aging. In this case, the signal can't be converted and sent to the brain properly, and unfortunately, the damage is usually permanent.
All right, we have covered a ton of ground. I think it's time to see how well all this information stuck. Let's test your auditory IQ with just a couple of quick questions. Ready?
First question. A jogger's out for a run. She hears a twig snap behind her right shoulder. She knows its location instantly because the sound reached her right ear just a moment before her left. What amazing ability does this demonstrate?
And the answer is D, sound localization. Her brain did that amazing GPS calculation using those tiny delays in time and loudness to create a perfect mental map of the world around her.
Okay, next one for you. An audiologist is explaining that one type of hearing problem is damage to the cochlea itself, while another is a physical blockage that stops sound from even reaching the cochlea. What are these two different conditions called? You got it. The answer is A. The blockage that stops the sound waves is conductive deafness. The nerve damage inside the cochlea is sensorineural deafness. It all comes down to where in the system the problem is.
And that brings us to our final thought for today. We've seen that hearing isn't just a passive recording of the world. It's an active, complex, and incredible construction happening inside our heads. It's kind of like a beautiful illusion. And it makes you wonder, doesn't it? What other parts of our reality, what we see, what we feel, are also being carefully and wonderfully crafted by our brains.